Sir. So when we put del A in the translation operator, then what happens is that it the L generates the rotation like the
Yeah,
result.
yeah, exactly. So the translation operator translate the system, you know, along the vector A, right? So suppose this vector is, say, it can be a very small vector, say delta A, and you can, so delta AI, and you can sum up all the delta AIs into a finite A, right? Now suppose that this finite A was 0 in such a way that this delta A is essentially, all these delta A's are very small vectors, essentially, inscribing a circle. Okay, we can do that, right? So if this is the case, then all these small delta A's, it's a delta A, we can write those delta A's as a small angle, say delta alpha. So this is delta alpha, times some, vector, say n, which is the vector coming out of the page, times the displacement vector or the position vector x. So the displacement, right? Do you agree with this?
Yes, sir.
Yeah.
Sir, a question. Does the arrow at which n points matter in this context? Like, will that
Well,
change?
it doesn't, because they're almost the same, right? I mean, if I zoom it up, then this is basically, you know uh, so this is probably the first arrow, yeah, and this little thing is delta A, right? So this arrow, this guy is, and this guy are almost the same, right?
Yeah.
Yeah. In the limit which is the limit we're going to take, we are going to take the limit where delta A goes to 0, right?
Mm-hmm.
Those two things will become the same,
Yeah. Okay.
right? So now, if I take this expression and I plug it into my, you know, into the expression for the translation operator, what do I get? I get U translation of, delta A, and that's e to the power minus I by h bar. তারপর এখানে হবে হচ্ছে গিয়ে ডেল্টা আলফা, তারপরে হচ্ছে n cross x dotted with p, right? Now this thing we can use one of the vector identities to write it as, remember all these triple identities that no one paid attention to in high school? So this
Sir,
can
what
be,
is
delta alpha is the small angle, this angle. Okay?
yeah?
Because we are using the arc length formula, right? The length of this thing is delta alpha times the modulus of x, right? That is the modulus of delta A. Okay, and this is the arc length formula, whose more famous version is r, c
So
equals to
S
2.
equals R theta.
Sorry? Yeah,
S
exactly.
equals R theta. I mean, the
Yeah,
arc length equals to the radius of the sector and times the angle subtended between them, theta.
exactly, but expressed in pi radians. Okay, so now what we want to do is that here's the crucial step, is that this becomes n dot x cross p, okay? And we know what this is, times this. This is the orbital angular momentum operator. So we can write this as the infinitesimal as minus I delta A, and then, or delta A can be, we can call this a delta A dot L. This is an operator, okay? So we see that the operator that translates an object through a small arc length of a circle, of a small arc of a circle, is generated by the angular momentum, orbital angular momentum operator. And because, L will...
Sir, how did we get delta A right from delta alpha?
Delta alpha times N is delta A. So, right.
There is a dimensional problem, I think so.
Right. I see. Yeah. There's a dimensional issue. You're right. IHL. Oh, sorry. Yeah, you're right. Yeah, you're right. Sorry. Sorry. Yeah. Now he is absolutely correct. Let's call this delta A n dot L. Delta alpha. Right. Yeah. Yeah. Are you happy?
Yes, sir.
Yeah. So now, all these, n dot L is the angular momentum in the particular direction, right? So if I choose my directions correctly, if I choose them in such a way, I can even call this, say, LZ. Okay. So what I want to say is that, this operator will commute with itself. So we can say U alpha, which is, rotation by the angle alpha, can be seen as, applying the translation operator a lot of times, to the power n, where n goes to infinity, and, this angle becomes smaller and smaller, right? And so there's a lot of application of these things here, right? Okay, so I have already multiplied it. So then we get a finite angle, rotation. So U alpha rotation is going to be e to the power minus I alpha, and then n dot L. And this is the rotation operator, okay? This rotates something, this translates something on a circle, because this is a rotation of an object around an axis that is outside its body. If we are to use a classical analogy, right? So pictorially, what is happening here is the following. Suppose that, we have an object, a system, and the system has some spin, and its spin is pointing in some direction. So this is the spin. And what we are doing is we are rotating it by some angle alpha, but we are not changing the orientation of the spin. This rotation is done by L, or I should really say L, because it could be just one L. Analogously, if I had done a rotation of the system, but by J, which is the total angular momentum operator, which consists a part which is both has L and J and S, so it is L plus S, then not only would we rotate the system, but we would also rotate the spin vector, such that this angle, this angle would remain the same. On the other hand, if I just do a rotation using S, then if my system started in this configuration, it'll change to this configuration. Only the spin will change, but it will not, the system will not translate. Over here, what we saw is that we saw that our system, our system did a translation. Here there was also translation, but here there is no translation. Okay? I mean, I haven't really proved these statements. This is a statement I will prove eventually, but but it's these kind of things stand to reason. Okay, so any questions? I know there are questions, so.
Sir, the angle at which the spin occurs, is it the same as alpha or different?
It'll depend on what angle you put in. Yeah, I mean, if you're using this, then of course it'll be the same angle. If you're using this generator, right?
Mm-hmm. Oh, okay.
Yeah, but you can do you can do this and then do this. So you can do different angles.
Then, separately, if we do this, then it will.
Yeah, then there will be a separate angle. Yeah.
Yeah. Okay.
I mean, these two degrees of freedom, the orbital angular momentum and the spin angular momentum, they are independent. There can be coupling between them. There can be interaction between them, but they're different. They live on different Hilbert spaces.
Oh, I see. Yeah.
They're subspaces of the bigger Hilbert space that your system is described by. We'll talk about composite systems and how to, and stuff like that. Okay, any more questions about this? Otherwise, I'll move on.